Hello dear students, welcome to another video on pen and paper chemistry where we deal with different topics in organic, inorganic and physical chemistry. And the only thing that the channel asks of you is to make sure that you have your pen and paper ready while you watch the videos here. In today's video, we continue with the topic of numericals made easy and fun. And this is video 2. In case you have missed out on video number 1, sincere advice to go back to it, because there we have listed the steps how to go about numericals in an easy way without being confused about a lot of data which is provided to you. And there were some questions which we had dealt with, and there were some questions that I had left for you to solve. So let's discuss those now. So the question was, calculate molality of the solution, molarity, mole fraction of each component in a 10% aqueous solution of glucose by weight. And now what we are going to do is, yes, we are going to tabulate the data. Now since we've got the solute as glucose, the molar mass of glucose you can calculate as 12 times 6. We go ahead with it, plus 12 plus 16 times 6, and we will have the value as 180 gram per mole. And what about the solvent? Yes, it's simple, that's water. So by now you must be, you must have by hearted it, right? Okay, we don't have something called as the molar mass of the solution because that's a mixture. We come to the mass of each of the components. Now it's a 10% weight percentage. That means I have got 10 grams of the solute in 100 grams of the solution. So that means what is the weight of the solvent that we've got? Yes, as simple as that, 90 grams. What other data has been provided to us? We need to find molality, molarity and mole fraction. The density of the solution has been given to us as 1.5. So that's a value pertaining to the solution. So I'm going to write it over here, gram per milliliter. Did you attempt this question? In case this is the first time you have come to watch this video, try and do this question yourself. So we've got molality as weight of the solute times 1000, molar mass of the solute, that is 180, multiplied by the weight of the solvent. Because I've already divided by 1000, that is why I'm going to just put the value in grams. So I get it over here, 90, which comes to approximately 0.61 molal, right? Okay, next one is molarity, capital M, that is weight of the solute, which is 10 grams divided by its molar mass times the volume of solution in liters. But do I have the volume of solution? No, I don't have. So how can I determine the volume of the solution? Yes, we've got the mass, we've got the density. So I'm going to find out the volume. Please go ahead and do it. So volume is equals to, go ahead, mass divided by density. So 100 grams is the mass of the solution, density is 1.5. I will probably just leave it like this. So that leaves me with 1000 upon 15. And what will be the unit? It will be milliliters, right? But in the formula, we have to put the value of volume in liters, if you remember the formula. So milliliters to liters. How do you convert milliliters to liters? You divide it by 1000. So divided by 1000. Now you realize why I didn't cancel it. So I will simply have it as 1 by 15. So 1 by 15, 15 goes into the numerator and I get the value as 0.833 molar. Please check the calculations. I've tried to do my best, but we are all human. we may go wrong. So please check and let me know in case there is any error in this. Okay, no, method is correct. Yes, sometimes in the calculations, that's why I'm asking you to check. The third part of the question says mole fraction, right? You've got to find out the mole fraction of each component. Now, if I go to the mole fraction, that means, let's say, mole fraction of the solute. That means number of moles of the solute divided by the total number of moles in solution. In other words, I need the number of moles of each component. So what I'm going to do is, I'm going to extend my chart over here and make one more column corresponding to number of moles. Okay, so number of moles is given by the mass divided by the molar mass, will be given by mass divided by the molar mass. So I get here 5 and here it will be 1 by 18. Now go ahead and find out the number of moles of the solute and the number of moles of the solvent. Notice over here that when I have to find out, oh, what am I doing over here? Why am I putting N? N is number of moles, right? Sorry, we have to find mole fraction. Yes. Good morning, ma'am. Please wake up. Yes, N2 upon N1 plus N2. Why did I do that? What was the mistake I was making? Mole fraction is denoted by the symbol X, right? So go ahead and now put the values of the number of moles. Instead of 1 by 18, you can take it as a decimal as well. I find it much more comfortable to deal with fractions. So you can do either way. So we will have over here x1 is equals to, okay, so 1 by 18 divided by 1 by 18 plus 5. That will give me the mole fraction of the solute, which comes to 1 by 18, 1 plus 90 divided by 18. So I will have over here 1 by 91, that is 0.01098 is the mole fraction. What will be the unit of this? Yes, correct, no unit. It's a fraction. It's a pure fraction. You're simply dividing the number of moles by number of moles. So what will be the mole fraction of the solvent? Either you can put the values over here. So in which case this will be 5 divided by 1 by 18 plus 5. And you get the value of 0.98901. Or do you remember that we said that the sum of mole fractions is always equal to 1. So I can also determine x2 as equal to 1 minus x1, which will again give me the same value, right? Now the next question is based on the concept of ppm, parts per million, which we discussed in the video on molarity, normality and terms related to concentration. If you are not familiar with this, I would request you to go through that video first in order to be able to understand this type of question clearly. Again, back to our sheet. And we've got the question, a sample of drinking water was found to be contaminated with chloroform, 15 parts per million by mass. That means I have got the weight of chloroform given to me as 15 parts in 10 to the power 6 parts of the solution, right? Now when I've got, that means I have to find out the mass percent. That means how much of chloroform is there in 100 grams of the solution. So that means 15 out of 10 to the power 6 parts, and how much would it be out of 100? Simple unitary method, and we get it as 15 into 10 to the power minus 4 grams, right? So this is the weight of chloroform that we've got in 100 grams of the solution. So let us jot down this data for our further reference. So I have got over here 15 into 10 to the power minus 4 grams, and the mass of the solution is 100 grams. So what would be the mass of the solvent? Yes, This is where it actually gets tricky, because it's going to be 100 take away 15 into 10 to the power minus 4. If you are using a calculator, then of course this becomes very easy and quick to solve. But in case you are not allowed to use a calculator, logarithms come in very, very handy, and you can solve these numericals very easily. And in case you want to understand logarithms, there are separate videos on the channel dealing with logarithms, the basics, as well as how to use logarithms in order to solve numericals easily. Okay, let's go back to our question. It says, what would be the molality of the given sample? Now what do you have to do? First, we need the molar mass of the solute. Please, can you find out the molar mass of the solute? Chlorine is 35.5. Atomic mass, carbon is 12, hydrogen is 1, chlorine is 35.5. You can also take it from the periodic table. And carbon 12, hydrogen 1, and chlorine 35.5 times 3. This is what we get as the molar mass. If I am not wrong, it's 119.5 gram per mole. Now the only thing left for us is to substitute in the formula or just apply the logic. So molality would be the weight of the solute, which is 15 into 10 to the power negative 4 grams, divided by the molar mass of the solute, which you calculated just now, multiplied by the mass of the solvent, but in kgs. Remember, this is in gram. So I have to divide the whole thing by 1000, in which case the 1000 goes into the numerator, and I will have to do 100 minus, I can write this 15 into 10 to the power minus 4. This is what it means. So I can write it as 0.0015, right? So see, even without the calculator, we are no less, we can still solve this question. Now you have to do the calculations. Either you can do manually or logarithms, anything. The closest, so the answer that we get to is 1.25 into 10 to the power minus 4 molal, right? In case you are hovering nearby, so something like 1.27, 1.24, it would still be accepted, but try not to waver off too much away. So something like 1.34 would not be accepted. So try and do your calculations step by step and clearly. Next question. Commercially available sample of H2SO4 is 15% H2SO4 by mass. So what information do I extract from here? That I've got 15 grams of H2SO4 in 100 grams of the solution. Simple. Next thing, its density. Now this density will be of the solution. So density is given to me as 1.10 gram per centimeter cube. Can be written as gram per cc or centimeter cube as well, right? Yes, it's a per centimeter cube. It's in the denominator. That's why the slash. Now, what is its molarity? That means I need capital M. I need the weight of the solute, the molar mass of the solute, the volume of the solution in liters. So I'm going to divide the volume in milliliters by 1000, because here I'm going to take it in milliliters. Or if you want, let me not confuse you, you can also simply put it as weight divided by molar mass into volume of solution in liters. Right? Now go ahead, put in the values. How do you know we really don't need the mass of the solvent, right? So I can do without this. What about the volume of this solution? You've got the mass of the solution, you've got the density of these solutions. So let's put another thing in this column, that is volume. Volume is mass divided by density. So 100 divided by 1.10 cc, and I will divide it by 1000 in order to convert it into liters. Correct? So let's put down the values now. So weight comes out as weight is 15 divided by molar mass. Oh, molar mass we did not calculate. Yes, we know it by now. Plus 32 plus 16 into 4 gives us a value of 98 gram per mole. Am I right in this one? So the molar mass is 98, volume of solution in liters. So if you see over here, we are left with 1/11, and 11 goes into the numerator, and we will have our answer as capital M, molar solution. Gives me a value of 1.684 molar. Please check. Next thing that you have to determine is molality. Again, weight, molar, and weight of the solvent in kg. So I will convert it into kg by dividing by 1000. 15 and 98, we already have it in place. What about the mass of the solvent? 100 take away 15. See, this is where the chart comes in so handy. I wish I had known this method when I was doing my grade 11, 12. It becomes so much easy, right? And the answer that I got was 1.8007 molar. Yes, our answers may differ slightly because, as I said, just to be doubly sure, I used a calculator to solve it. 1.8007 molar. Please don't forget the unit. There's a third thing as well in the question. It says you have to find out the mole fraction of solute in the solution. Again, mole fraction, this time I'm not going to make a mistake for sure. N1 upon N1 plus N2. And what is wrong if I make a mistake? We all learn by making mistakes, right? So N1, so I need to find out the number of moles. How do I find out the number of moles? I need to extend this table. Mass divided by molar mass, and here molar mass of water is 18. Yes, we've by hearted it by now. Correct. 85 by 18. What do you have to do now? Simple. You have to substitute the values. 15 by 98 upon 15 by 98 plus 85 by 18. Convert it into decimals, and the answer is 0.03138. What is the unit? Yes, no unit. It's a pure fraction. As I said, there could be slight difference in answers, 0.0, depending upon the number of significant figures that we have taken in order to solve these fractions. So something like 0.031, 37, 36 would still be acceptable, but yes, you have to check with your curriculum masters as to what they say, what is the acceptable rule. Okay, I added one more question over here. I had given you till question number 6 to practice. Now go ahead, there's another one. So that's an impromptu question. What is the molarity of a solution obtained by mixing 300 ml of 0.5 molar NaOH and 200 ml of water? Okay, let me make it more clear. 200 ml of pure water. Okay, I think this should be clearer now. Think about it. You've already been given molarity, but you are again being asked to find out the molarity of this solution. Then what is this molarity of? What it says is that you've already got a 300 ml solution of NaOH. It's a solution which has a molarity of 0.5 molar NaOH. Now what you do is you are adding 200 ml of pure water in this. Now when you add 200 ml of pure water, that means the total volume of the solution is going to change, and that is going to become 300 plus 200, that gives me a value of 500 milliliters. Since the total volume of the solution is going to change, so definitely the molarity is going to change. Now we need to see, did we add more NaOH to the solution? Did we add more solute to the solution? No, we didn't. So how are we going to tabulate? So let's do before and after. I have got the weight of the solute. I don't know the weight of the solute, so let's say it's X only. And even after adding water, the weight of the solute still remains X. What about the molar mass? Right, now I've got NaOH over here, but since I'm going to take it as mm, right, after. Now what about the volume of the solution? Now before it was 300 milliliters, and after adding water it is 500 milliliters. What about molarity? Now this was 0.5 molar before, and now I have to find out. Notice something interesting over here in the question. The number of moles, that means if I find out N over here in this question, so N, that is the number of moles of the solute. Again, I am talking only about the small n. Remains X by M and remains X by M. Does it lead you anywhere? Does it give you a clue as to how we are going to do the question? Because we said that molarity is number of moles divided by the volume of solution in liters. Right? Now first one, molarity is M1, number of moles is N, the volume of solution in liters when we started with it was 300 divided by 1000. Why 1000? Because we have to convert it into liters. After adding water, molar, and by the way, this is given to us as 0.5. Now M2 again, N divided by, now the total volume of the solution is how much? 500 ml, because now that water is a part of the solution. So I'm going to put over here, oh, there isn't to be a multiplication, right? So we have 500 divided by 1000, and the molarity here is M2. So if you notice over here, N and N is the same in both of them. I can simply put it, I could have, just simply put it as N over V, right? So number of moles can simply be given as molarity into the volume. Number of moles is remaining the same, so M1 V1 is equals to M2 V2. The number of moles before adding water is equals to the number of moles after adding water. But what is going to change? The molarity is going to change. But remember, apply logic. We have not added more NaOH. If we were adding more NaOH to the solution, then yes, the number of moles are also going to change. Then you cannot work it like this. So you'll find out the number of moles and then calculate the molarity. Now it's easy, right? Go ahead and solve it. If you've understood the logic of this, then you can directly go on to substitute the values. So I'm going to put over here molarity earlier was 0.5. Volume, I'm going to put it directly as 300. I'm not changing. If you see over here, the volume, both of it is in milliliters. So if you are wanting to go the fast way, no need to convert it into liters, because you will anyway cancel it. Okay, 500 by 1000. Now calculate. M2 comes out as 0.3 molar. Got it? 1000 is the same on both sides, 100 is the same on both sides. M2, you can do the calculations your own way. Each one of us have different ways of doing, and each one of us are comfortable in different ways. But the answer to this would finally be the new molarity of the solution is 0.3 molar. You see over here, when you have increased the volume, the molarity has gone down to 0.3 molar, because the number of moles of, the volume of the solution has increased. So the number of moles present per unit volume of the solute is actually going to decrease in a given volume. The total number of moles hasn't changed, but the number of moles in the given volume has changed. Now, before we end the session and go for a short summer break, I would like to introduce to you these flow charts, these diagrams, which I've introduced on the channel to make learning chemistry easy and fun for grade 11 and 12. So you'll find these flow charts which make learning organic chemistry, not just learning, understanding, remembering, recalling organic chemistry and many other topics easy and fun. You'll find zoomed pages as well on both the site Pen and Paper Chemistry as well as on the channel Pen and Paper Chemistry on YouTube. So please do stay connected and make full use of this till we meet again after a short summer break. Till then, stay happy, stay healthy.